also supervised by phasor model. So yeah, I'm going to talk about how we constrain the redshift evolution of IGM neutral fraction during the cosmic reionization using the 93 quasars that Simon previously mentioned. So I will first give a very brief introduction on the reionization and also how we constrain the reionization using quasars. And then I will also introduce about our Shokes quasars, and then I'll talk about our results. So basically we know that after cosmic dark age, the first stars and galaxy formed, and they emit UV photon to ionize those neutral intergalactic medium. And as more and more stars and galaxies form, there will be more and more ionized region. Until the end, all the ionized region overlapped. All the IGM gets ionized. This is called the reionization. And basically, we can write it down as this equation: how fast the IGM being ionized depends on how fast the ionizing sources can produce photon, and also how fast the IGM can combine back into neutral. And this basically depends on things like the source properties, like the escape fraction of ionizing photon of the high-redshift galaxy, or things like the confidence factor of IGM. But observationally, we still know a little about reionization, because first it's because it's just too difficult to observe an object at very high redshift, and also it's because at redshift higher than 5, before the end of reionization, the IGM is just too neutral, so they can absorb most of light from the high redshift object. So still we don't know when the reionization happens and what ionized the intergalactic medium. And here I show the current observational progress on the redshift evolution of the mean neutral fraction of IGM. So you can see that at redshift around 5 to 6, the neutral fraction is well constrained by the Lambda alpha absorption in quasar spectrum. But when you go to redshift higher than 6, you can see that the constraint here is quite loose. It is because of the small sample size. And also, if you want to constrain the IGM using the high redshift galaxy, it requires mainly assumption on the like the property of this galaxy and the population of them. So still we don't know much about the reionization at redshift higher than 6. But now, because more and more quasars, these redshifts are being discovered, so we can have a tighter constraint on it. And this is what I'm going to talk about in my talk. And some other advantage using quasar to constrain reionization are first that the quasars are bright, so we can easily observe their spectrum. And also because we measure the neutral fraction, directly use the Lambda alpha absorption due to the neutral hydrogen in quasar spectrum. So we don't have to assume things like the population of quasars or their like properties. And also, if we have as many quasars as possible as a background light, we'll be able to map the distribution of IGM neutral fraction at a certain redshift. So, for example, we can if we have many quasars at redshift higher than 6, then we can measure the neutral fraction at redshift 3, and this is very important. And we can measure things like the fluctuation of neutral fraction, not just the main IGM neutral fraction. And this is very important because actually different source population would cause different fluctuation of neutral fraction. For example, if the fluctuation of UVB, the ionizing field, is dominated by galaxy, then the neutral fraction distribution will be looked like this. But if it's dominated by quasar, then it will be looked like this. And we can measure the fluctuation of this using the Lambda alpha absorption in quasar spectrum. And the way we measure it is by observing the UV spectrum of quasars. So you can see that the observed spectrum is the white one, and the intrinsic continuum is the blue one. When you compare the observed one to blue one, you can see that there are many absorptions. These are due to the foreground neutral hydrogen, and these are Lambda alpha absorptions. So we can measure the redshift of this absorption by dividing the observed wavelengths by the Lambda alpha wavelengths. And also we can measure how neutral it is by comparing the observed flux by the intrinsic one, which is the transmission here. And then you can convert the transmission to optical depth, and then further convert this into neutral fraction. And the other way to measure neutral fraction is you can look closer to this region. You'll see that there's some transmitted flux here near the quasar Lambda alpha emission, and these flux are due to the strong radiation field by the quasars, and we call it the quasars ionized bubble. And this ionized bubble, the size of the ionized bubble basically is scaled with the quasar emissivity, quasar lifetime, and the neutral fraction. So we expect to see a smaller ionized bubble in a mostly neutral IGN, and a very large ionized bubble in a very ionized IGN. So in the spectrum, we can see that from quasars to the outer part of the H2 bubble, there is a steep drop of the transmitted flux. So we can simply measure the distance from quasars to the edge of the transmitted flux. And the sample we use have been mentioned by Simon, which are the Schultz quasars. So the Schultz project basically aim to find the low luminosity quasars, and because the population of low luminosity quasars is larger than the brighter one, so we will be able to constrain the reionization using more quasars. And so far, there are already 93 quasars being discovered over the from the 900 degrees square sky over the 1400 that is going to be surveyed by HC. And these 93 quasars already take half of the non-quasar population at redshift higher than 5.5. And here I show the UV spectrum of the quasars. These spectrum are taken by either GTC or Subaru. So these quasars are spent at redshift 5.6 to 7. So here is the stacked spectrum from redshift 5 to 7. And but one thing we have to notice that the resolution of this spectrum are actually quite low, and also the SN ratio is also low. So we cannot do a very precise measurement using these quasars. And so this is one of our major results, which is the Lambda alpha transmission as a function of redshift measured from the Schultz quasar. So here we can see that the transmission here drops down to 0 at redshift around 6, and at higher redshift the transmission becomes consistent with 0. That means at redshift higher than 6, the neutral fraction of IGM is just higher than 10 to the minus 4. So we can say that after redshift 6, because the IGM is becomes mostly ionized, so we can say the redshift 6 is the end state of the reionization. And to further constrain the neutral fraction at high redshift, we use the bubble size. But in fact, there's two different definitions of bubble size, which is REQ and RNZ. This one is more commonly used because it's easier to measure the near-long size or the bubble size using this definition, which is the distance from quasar's Lambda alpha emission to where the transmission first drops down to 0.1. So this is an example. So you can see that using this definition, you measure near-long epsilon here. And the second definition is the REQ, which is defined as where the photoionization rate due to quasars equals the UV equals the background photoionization rate. and this is more physically motivated, but it requires us to, but we have to assume a fixed quasar emissivity and fixed quasar lifetime to measure the neuron size. But this could be used to infer the background photon emission rate, and compared to this one, the RND can only, it is found to be insensitive to the neutral fraction, but so we can only use it to infer the quasar lifetime. And here I show the neuron size, the MS bubble size measure using the second definition, which is where the distance from quasar to where the transmission is 0.1. And we found that if you fit the redshift evolution of neuron size using our short quasar X redshift higher than 6, then you found the quite shallow evolution, which is the red dashed line here. And this is consistent with the bubble evolution of quasars with quasar lifetime of around 10 to the 6 or 10 to the 7 years. That means most of the quasars we found are not very young, but still you can see that there are some quasars with very small ionized bubble size, and this could be very young quasars, or it could be the neurons, the quasars which is blocked by a very neutral IUN. The neuron size measured using the first definition could be used on inverse the photon emission rate, which is shown here, and the red ones are our measurement. So you can see that there's a steep drop of the photon emission rate at redshift around 6. And our result is consistent with these two models, the gray one and the blue one. And these two models are the photon emission rate evolution by assuming a high redshift fence dominant gas dominated reionization. So what we can tell from our result here is that our result is more consistent with reionization due to the fence high redshift gas. So I will leave my slide, my summary here. Thank you very much.
Thank you very much for nice talk. We have 2 minutes for Q&A. Is any questions? Either from online or offline.
So can I ask? So if you use if you compare REQ and RNG, REQ gives you much smaller values. So if you plot the size evolution with REQ, you get what do you get?
It depends on the neutral fraction. But what I get is the size of REQ grow as a function. The size is larger at higher redshift. And yeah, but if you plot only the size is smaller at higher redshift, and currently I haven't found out reasons.
So say that again. What at high redshift?
I found the larger size of RE2 at higher redshift, but the uncertainty is quite large. And also the REQ depends on the quasar luminosity, so it's quite hard to tell say anything about the neutral fraction. Simply use the size.
Okay. Any other questions?
Oh, okay, it is please. So in RNZ, how do you choose the value of tau net?
This tau is basically measured using, it just converts from per transmission equals 0.1.
Oh, I can see that. Okay, thank you.
Okay. I have one quick question. So you now measure the redshift at 6. So in order to go to further higher redshift, so what do you want to do? So you wanna go higher leaderships, right?
Yes.
So what should we do?
We use other observation or
Yes.
observe fainter quasars.
Mm-hmm.
I think in terms of quasar, we can try to observe fainter one, but I don't know whether there's any survey on finding fainter quasar than these two quasars.
Okay, thank you very much. It's time to go next speaker.